Hello, in this video, we are going through the OCR 2023 A Level Chemistry, Paper 2, Synthesis and Analytical Techniques, question by question. I'll show you not just the answers, but how to think through them the way the mark scheme expects, so you know exactly how to pick up marks in the exam. If you want, pause and try each question yourself before listening to the explanation. That's where the real learning happens. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. Let's get started. We start with section A. In the first question, we are asked which of the four compounds given is used for proton exchange in NMR spectroscopy. In proton NMR, proton exchange is the process where certain protons are swapped with deuterium. The protons swapped are typically attached to electronegative elements like oxygen and nitrogen. The first option is carbon tetrachloride. It is used as solvent for proton NMR, but it does not facilitate proton exchange. This is not the right answer. The second option is deuterated chloroform, also a common NMR solvent, but it does not promote proton exchange. This is not the right answer. The third option is deuterium oxide. It enables proton exchange, replacing labile protons with deuterium, causing their signals to disappear from the proton NMR spectrum. This is the correct answer. In the fourth answer, we have tetramethylsilane or TMS. It is used as a reference compound in NMR, providing a sharp peak at 0 ppm for calibration. It does not participate in proton exchange. This is also not the right answer. Then, the answer is C. In question 2, we are asked which of the four given compounds reacts with 2,4-dinitrophenyl but does not react with Tollens reagent. The reaction with 2,4-dinitrophenyl confirms the presence of a carbonyl group, meaning the compound is either an aldehyde or a keton. Since it does not react with Tollens reagent, it must be a keton, as Tollens test is specific for aldehydes. Drawing the structure can help identify the keton more easily. In option A, we have a keton and no aldehydes. This can be the right answer. In option B, we have an aldehyde that will react with Tollens reagent. We can discard it. In option C, we also have an aldehyde. We can discard it. In option D, we have an alcohol that will not react with 2,4-dinitrophenyl. We also discard it. The answer is A. In question 3, we are given the structural formula of propyne, a member of the alkynes homologous series with the triple bond functional group. We are asked to determine the general formula of alkynes from the four given options. The general formula for alkynes is option B. If unsure, write the molecular formula of the given compound, C3H4, and compare it to the given choices. By matching the format, you confirm that the correct general formula is CnH2n-2. The answer is B. In question 4, we are given the structure of paracetamol. We are asked to identify the structure from the four given. In this type of problems, help to mark the functional groups. We have a phenol and an amide. The answer is C. In question 5, we are given the structure of the oxymetazoline. We are asked how many atoms of hydrogen are in one molecule of oxymetazoline. Labeling the number of hydrogen atoms in each carbon helps. I get a total of 24. The answer is B. In question 6, we are asked which statement of the forgiven supports the delocalized model of benzene and not the K-Coulé model. The delocalized model of benzene suggests that all carbon-carbon bonds are equal in length. In contrast, the K-Coulé model proposes alternating single and double bonds, which would result in different bond lengths. However, experimental evidence shows that benzene has uniform bond lengths, supporting the delocalized model over K-Coulé structure. The answer is B. In question 7, we are asked by the systematic name for a given compound. We begin by identifying the longest carbon chain, which consists of 8 carbon atoms. Next, we number the carbon atoms to ensure that substituents are assigned the lowest possible positions. If we number from the left, the lowest positioned radical is 2-ene. However, if we number from the right, we get 1-ene, which takes priority according to naming conventions. Therefore, we start numbering from the right to correctly name the compound. The molecule has methyl groups at positions 3 and 5 and double bonds at 1, 3, and 6. So, following the naming rules, the proper name is 3,5-dimethylocta 1,3,6-triene. The answer is A. In question 8, we have that for complete combustion, 0.1 moles of an alkane requires 22.8 cubic decimeters of oxygen measured at room temperature and pressure. We are asked which of the 4 provided alkanes has undergone complete combustion. We start by calculating the number of moles of oxygen consumed. As 1 mole at room temperature and pressure occupies 24 cubic decimeters, then 22.8 cubic decimeters is 0.95 moles. We then calculate the ratio of alkane to oxygen for each complete combustion. For 1 mole of pentane, we need 8 moles of oxygen. For 1 mole of hexane, we need 9.5 moles of oxygen. For 1 mole of heptane, we need 11 moles of oxygen. For 1 mole of octane, we need 12.5 moles of oxygen. With this proportions, we can see that for 0.1 moles of hexane we need 0.95 moles of oxygen. The answer is B. In question 9, we are asked which compound of the 4 given has the greatest number of peaks in its proton NMR spectrum. To determine which compound has the greatest number of peaks, we need to identify unique proton environments and count the number of distinct signals. In option A, we have a symmetrical molecule. We have methyl groups on both ends producing one environment. We also have CH2 groups next to the CO, producing another environment. These give a total of 2 NMR peaks. In option B, we also have a symmetrical molecule. 2 CH2 groups next to the bromine atoms and giving one environment. We also have internal CH2 groups giving another environment. These produce 2 peaks. Option C is another symmetrical molecule. We have the hydrogen in the carboxyl groups, giving one environment. We have a hydrogen in the central carbon, producing another peak. And we have a third peak from the hydroxyl group from the central carbon. We have 3 peaks. Finally, we have option D. The 3 methyl groups are equivalent due to symmetry and produce 1 peak. We have a carbonyl group producing another peak. We have a total of 2 peaks. We have that the greatest number of peaks in the proton NMR is option C. The answer is C. In question 10, we are asked which of the 4 given esters is most likely to produce a mass spectrum with a fragment ion at mass over charge equals 43. The esters given are combinations of hydrogen, carbon, and oxygen. The most probable ions that could give mass over charge equals to 43 are C3H7+ and C2OH3+. Looking at the given structures, we can easily identify the propyl group in option B that gives a mass over charge equals to 43. While other esters might, in theory, yield fragments of mass over charge equals to 43 through more intricate rearrangements or multiple bond cleavages, the direct scission of the propyl group in ester B represents a highly probable fragmentation. This makes ester B the most likely candidate. The answer is B. In question 11, we are given the infrared spectrum of an organic compound. We are asked to identify the compound which could have produced this spectrum. From the data sheet of the spectrum, we can identify the following peaks. The peak at around 3,500 reciprocal centimeter is a single oxygen-hydrogen bond from alcohols or phenols. The peak at around 3,000 reciprocal centimeter is a single carbon-hydrogen bond from alkyl groups, alkenes, and arones. The peak at around 1,700 reciprocal centimeter is a double carbon-oxygen bond. The peaks below 1,500 reciprocal centimeter are fingerprints. We now check the different compounds given. Option A has a carboxylic group. This is characterized by a broad peak between 2,500 and 3,300 reciprocal centimeters. We have peaks in this region, but they are not broad. We discard option A. Option B does not have single oxygen-hydrogen bond. We discard option B. Option C has single oxygen-hydrogen bond, carbon-hydrogen bond and double carbon-oxygen bond. Option C could give the profile shown. Option D does not have a double carbon-oxygen bond. We discard option D. The only option that fit the profile is C. The answer is C. In question 12, we are asked to identify the compound, from the four given, that react with ethanol chloride. Ethanol chloride, like other acyl chlorides, reacts with water, ammonia, primary amides, and alcohols. Among the four given compounds, only option D falls into one of these reactive categories, as it is an amine. The answer is D. I leave a link in the description to the OCR reactions pathways, very useful to prepare for this exam. In question 13 we are asked which compounds is or are aliphatic from the three given. Aliphatic compounds are organic molecules that consist of carbon and hydrogen arranged in open chains or non-aromatic rings. They can be saturated, alkanes, or unsaturated, alkenes and alkynes, depending on the presence of single, double, or triple bonds. From the given structures, compound 1 is an open chain. It is an aliphatic compound. Compound 2 is a non-aromatic ring. It is an aliphatic compound. Compound 3 is an aromatic ring, cyclic structure with delocalized electrons. It is not an aliphatic compound. Therefore, compounds 1 and 2 are aliphatic compounds. The answer is B. In question 14 we are asked which compound or compounds is or are hydrolysed by aqueous hydrochloric acid to produce butanoic acid. Drawing the structure of the butanoic acid helps. Compound 1, methyl butanoate, is an ester. Esters undergo acid-catalyzed hydrolysis to produce a carboxylic acid and an alcohol. In this case, methyl butanoate hydrolyses to produce butanoic acid and methanol. Compound 1 produces butanoic acid. Compound 2, pentanenitrile, is a nitrile. Nitriles undergo acid-catalyzed hydrolysis to produce a carboxylic acid and an ammonium ion. If we count the carbons in the starting nitrile, there are 5 carbons. Hydrolysis of this nitrile will produce pentanoic acid, not butanoic acid. Compound 3, 1-chlorobutane, is an alkyl halide. Alkyl halides can undergo hydrolysis, nucleophilic substitution, in the presence of water to form alcohols, especially with strong bases. Under the given conditions, we can expect no reaction or very little reaction to produce some butanol, not butanoic acid. Compound 3 is incorrect. Therefore, only compound 1 produces butanoic acid. The answer is D. In question 15 we are asked which ion or ions contain bond angles of approximately 120 degrees. In ion 1, acetate ion, the carbon atom in the carboxylate group is sp2 hybridized, leading to a trigonal planar geometry with bond angles of approximately 120 degrees. Ion 1 fits the profile. Ion 2, phenoxide ion, consists of a benzene ring with an oxygen atom attached, which carries a negative charge. The carbon atoms within the benzene ring are sp2 hybridized, and the bond angles within the ring are approximately 120 degrees. Ion 2 also fits the profile. Ion 3 is a tert-butyl carbocation. The central carbon is a carbocation with 3 groups attached and no lone pairs. This leads to sp2 hybridization and a trigonal planar geometry around the central carbon with bond angles approximately 120 degrees. Ion 3 also fits the profile. Therefore, ions 1, 2, and 3 contain bond angles of approximately 120 degrees. The answer is A. We start with Section B. Question 16 is about hydrocarbons. In Part A, we are provided with a table with the boiling points of some hydrocarbons containing 6 carbon. We are asked to state and explain the trend in boiling points shown by these hydrocarbons. If we draw the structural formula of the hydrocarbons, we can see that the trend is that the boiling point increases as the hydrocarbons become less branched. Explanation. All 3 hydrocarbons are isomers with the same number of electrons. The only intermolecular forces present are London dispersion forces. Less branched molecules have a larger surface area, allowing for greater surface contact between molecules. More branched molecules are more compact, reducing this surface contact. Greater surface contact leads to more frequent and stronger London dispersion forces between molecules. More energy is then required to overcome these stronger London dispersion forces, resulting in a higher boiling point for the less branched hydrocarbons. Part B of question 16 is about the reaction of 2-methylpentane with bromine by radical substitution. In the first question, we are asked to complete a given table to show the mechanism for the formation of 3R-bromo, 2-methylpentane and 3 possible equations for termination. We are asked to use structural or skeletal formulae and dots for the position of radicals in the equations. The initiation starts with the formation of bromol radicals from molecular bromine with UV light. In the propagation, we need to ensure that we use radicals in the reactants and we have radicals in the products. So, we can have the 2-methylpentane reacting with a bromine radical to produce 2-methylpentane 3-il and hydrobromic acid. Another reaction is the reaction of the 2-methylpentane 3-il with bromine to produce 3R-bromo, 2-methylpentane and bromol radical. In the termination, we need to ensure that there are no radicals in the products. We can have the reaction between 2 bromol radicals to produce molecular bromine. We can also have the reaction of the bromol radical with the 2-methylpentane 3-il to produce 3R-bromo, 2-methylpentane. A third reaction is 2 radicals 2-methylpentane 3-il to produce 3,4-diethyl 2,5-dimethylhexane. The second question of Part B of question 16 says that the organic compound A is formed by the substitution of all 14 hydrogen atoms in 2-methylpentane by bromine atoms. We are asked to write the equation, using molecular formulae, for the formation of compound A from 2-methylpentane. The reaction is straightforward, just bear in mind that the reaction produces hydrobromic acid and not hydrogen. In the third question, we have that organic compound B is formed by the substitution of some of the 14 hydrogen atoms in 2-methylpentane by bromine atoms. 0.86 for 9 grams of compound B is heated until it is vaporized. Under the conditions used, compound B has a volume of 72 cubic centimeters and the molar gas volume is 40 cubic decimeters per mole. We are asked to determine a possible molecular formula of compound B. With the volume and the molar gas volume, we can find that the number of moles of compound B is 1.8 by 10 to the power of -3 moles. Dividing the mass of compound with the number of moles, we get a molar mass of 480.5 grams per mole. As the formula of compound B is CH14-XBrX, we can figure out the number of atoms of bromine using the atomic masses of the carbon, hydrogen, and bromine. We get 5 atoms of bromine. The molecular formula is C6H9Br5. Question 17 is about alcohols. In Part A, we have an unsaturated alcohol with 6 carbon atoms, containing 1 carbon-carbon double bond. We are asked to construct an equation for the complete combustion of this alcohol. An easy way to figure out the formula for this alcohol is to sketch out an example that fits the description. 6 carbon atoms. 1 carbon-carbon double bond. 1 hydroxyl group. Any example will do. I write hex 3en1 lol. Counting the atoms I get C6H12O. Complete combustion means that the alcohol reacts with oxygen to produce carbon dioxide and water. We balance the equation step by step. Carbon, there are 6 carbon atoms in the alcohol, so we need 6 molecules of carbon dioxide to balance the carbon. Hydrogen, there are 12 hydrogen atoms in the alcohol, so we need 6 molecules of water. Oxygen, in the products, we have 12 atoms of oxygen due to 6 atoms of carbon dioxide. 6 atoms of oxygen due to 6 atoms of molecules of water. These give a total of 18 atoms of oxygen on the right. On the left side, the alcohol contributes with 1 oxygen atom. This means that the remaining 17 oxygen atoms must come from the molecular oxygen. To remove decimal places, I multiply the reaction by 2 and get that 2 moles of alcohol reacts with 17 moles of oxygen to produce 12 moles of carbon dioxide and 12 moles of water. In Part B, we have compound C that is refluxed with excess acidified potassium dichromate 6 to form a single organic product and 1 other product. We are asked to complete the equation for this reaction. We have the oxidation of an alcohol containing primary, secondary, and tertiary alcohol groups. The oxidation behavior varies depending on the type of alcohol. Primary alcohols oxidize to form carboxylic acids, passing through an intermediate aldehyde stage. Secondary alcohols oxidize to produce ketones. Tertiary alcohols do not undergo oxidation under these conditions. To help with the exam, you can label the carbons in the structure or write the structural formula. Skeletal formulas can be harder to interpret at the beginning. With this information, we know the single organic product. The next step is to balance the reaction. The second product of the oxidation of alcohols under the given conditions is water. This is the mentioned 1 other product. We have lost 4 atoms of hydrogen in compound C, then we need 2 molecules of water to account for these hydrogens. Finally, we balance the oxygen atoms by adding molecules of oxidant. In the reactants, we have 3 atoms of oxygen from compound C. In the products, we have 4 atoms of oxygen in the organic compound, and 2 atoms of oxygen given by 2 molecules of water. This gives a total of 6 atoms of oxygen. To balance the atoms of oxygen, we add 3 molecules of oxidant. In Part C of Question 17, we are given a compound D that is refluxed with sulfuric acid as an acid catalyst to form a mixture of 3 isomers with the molecular formula C7H10. In the first question, we are asked to draw the structures of the 3 isomers of C7H10 formed from compound D. The conditions given produce the dehydration of the alcohol and form double carbon-carbon bonds. Note that C7H10 does not contain oxygen. I use structural formula, easier to see what is going on. We can see that there are not double bonds inside the ring. The removal of the OH group on the left can produce a carbon-carbon double bond in 2 positions, outside the ring or inside the ring. Due to the geometry, the 2 possible substitutions inside the ring are equivalent, as we will see in a moment. I only draw one. The removal of the OH group on the right can only be done inside the ring. Also, due to the geometry, the 2 possible substitutions inside the ring are equivalent. The combination of these structures yields 3 isomers. Ensure the drawings are distinct, avoiding mirrored or rotated duplicates. In the second question, a student converts compound D into a diodoalkane. We are asked to suggest suitable reagents for this reaction. This is a substitution to form a halogenoalkane. The halogen in this case is iodine. The reagents are sodium iodide or potassium iodide with sulfuric acid. In Part D of Question 17, we have the statement saying that there are 4 structural isomers of C4H10O that are alcohols. A student predicts that these structural isomers could be distinguished using carbon-13 NMR spectroscopy. We are asked to explain whether the student is correct. In the answer, we need to show how the peaks in the carbon-13 NMR spectra are linked to the structure of each alcohol isomer. In a carbon-13 NMR spectrum, each distinct peak corresponds to a carbon atom in a unique chemical environment. The 4 possible isomers alcohols are butan-1-ol, butan-2-ol, 2-methylpropan-1-ol and 2-methylpropan-1-ol. In the case of butan-1-ol, we have 4 carbons with 4 different environments, therefore, we have 4 peaks. In the case of butan-2-ol, we also have 4 carbons with 4 different environments, giving also 4 peaks. While both butan-1-ol and butan-2-ol would show 4 peaks, the chemical shifts of these peaks would be distinct due to the different environments of each carbon. In the 2-methylpropan-1-ol, we have 3 carbons with different environments, giving 3 peaks. And finally, in the 2-methylpropan-2-ol, we have 2 carbons with different environments, as all the CH3 carbons are equivalent. This gives 2 peaks. Therefore, the student is correct. Question 18 is about the preparation of 1,3-dinitrobenzene by a provided method. In Part A, we are asked to outline the mechanism for the reaction in the provided method, including the role of sulfuric acid as a catalyst. The reaction is an example of an electrophilic substitution. The first step is the generation of the nitronium ion. Sulfuric acid is a much stronger acid than nitric acid. The sulfuric acid acts as a proton donor, and nitric acid acts as a base, accepting a proton-forming protonated nitric acid that is highly unstable and decomposed to form nitronium ion and water. In the second step, we have the attack on nitrobenzene by the nitronium ion and the formation of a sigma complex. In the final step, we have the regeneration of aromaticity when the intermediate loses a proton, restoring the aromatic structure and yielding 1,3-dinitrobenzene. Role of sulfuric acid as catalyst. The protons restore the sulfuric acid, that acts as a catalyst to produce nitronium ions, and it is reformed at the end of the reaction. In Part B of Question 18, we are asked to calculate the percentage of 1,3-dinitrobenzene, giving the answer to 3 significant figures. We can calculate the yield using the number of moles or the masses. Both methods give the same result. Here I choose to use mass for the calculation. The molecular masses of nitrobenzene and 1,3-dinitrobenzene are 123 and 168 grams per mole respectively. With the given density of nitrobenzene, we can get that 12.5 cubic centimeters are 15 grams of nitrobenzene. Since 1 mole of nitrobenzene yields 1 mole of 1,3-dinitrobenzene, using the molecular masses, we get that 15 grams of nitrobenzene should produce 20.487 grams of 1,3-dinitrobenzene. But as we only get 15 grams, the yield, to 3 significant figures, is 73.2%. In Part C of Question 18, we are asked to describe how to purify the crystals obtained in Step 3. The first step is to dissolve the impure crystals in the minimum volume of a hot solvent like water or an appropriate organic solvent. Then, allow the solution to cool to room temperature to form pure crystals. Follow by filtering the mixture under reduced pressure using a Buchner funnel and flask. In the final step, the crystals are dried in air or in a warm environment, avoiding any drying agents. Drying agents are commonly used to remove small amounts of water from organic liquids. However, in the case of solid crystals, they are unnecessary and could interfere with purity. In question 19 we are provided with flowchart of the synthesis of compound Z performed by a student. We are asked to plan this synthesis showing reagents, the structures of intermediate 1 and intermediate 2, and equations. To transform the initial compound into compound Z, two key chemical changes occur. First, the transformation of a double carbon-carbon bond to single carbon-carbon bond with bromine addition. This transformation is achieved through a reaction with hydrogen bromide, which we'll call reaction 1. Second, we have the transformation of the bromine to aminomethyl group. This is not a single step, it requires two successive reactions. It starts with the addition of cyanide in methanol to form a nitrile group, I call this reaction 2. It is followed by the reduction of the nitrile into an amine using hydrogen with nickel as catalyst, I call this reaction 3. Let's work through the synthesis in stages. We begin by using reaction 2 to replace the existing bromine with a nitrile group. If we were to use reaction 1 first, we'd introduce a bromine that would then be removed when reaction 2 is applied later. Then in stage 1, the reagents are cyanide in ethanol and the equation is 3R-bromo-prop-1-ene reacts with cyanide to produce but 3-lenonitrile and bromide. The but 3-lenonitrile is the intermediate one. If we used reaction 3 at this point, it would reduce both the nitrile group and the carbon-carbon double bond, preventing us from later inserting the bromine via reaction 1. Therefore, reaction 1 must be used next. In stage 2, the reagent is hydrogen bromide and the reaction is the but 3-lenonitrile reacting with hydrogen bromide to produce 3-bromobutanenitrile, that it is the intermediate 2. Finally, we have left with reaction 3. Then, in stage 3 we use this reaction. The reagents are hydrogen with nickel catalyst and the equation is 3-bromobutanenitrile with hydrogen to produce for the bromobutan a 1-amine. Question 20 is about aromatic compounds containing the carboxylic and hydroxyl functional groups. In Part A, we are given the formula of the acetylic acid and we are asked to complete the given flowchart for the reactions of salicylic acid by adding the organic products in each box. When salicylic acid reacts with bromine, bromine atoms are added to the benzene ring via a substitution reaction. The marking scheme allows for bromine substitution at any position on the ring and permits a product with up to 4 bromine atoms attached to the ring. The marking scheme gives as answer the 4-bromo 2-hydroxybenzoic acid, but other example will work. The reaction with sodium carbonate, Na2CO3, is a neutralization reaction. The reactivity is due to the carboxylic acid group, COOH. The hydroxyl group, OH, is a weaker acid compared to the carboxylic acid group, and sodium carbonate is not a strong enough base to effectively deprotonate the hydroxyl group. The product obtained is the sodium salt of the salicylic acid. The reaction with propanoic anhydride produces an ester and an acid. The ester is formed when the propionyl group from the anhydride attaches to the OH group of salicylic acid. The acid is propanoic acid, the other part of the anhydride molecule. Part B of question 20 we are given the structure of the antibiotic paraaminosalicylic acid or PAS, used to treat several diseases including tuberculosis. A student predicts that PAS could polymerize to form a polymer containing both ester and amide linkages. We are asked to draw a section of this polymer. The section should contain one amide and one ester linkage, which should be displayed. Each PAS molecule has an amine, hydroxyl and carboxyl groups. With these groups we need to create an amine group and an ester group. As we are going to create 2 new links, we are going to use 3 benzene groups. Let's start with the creation of an amine group between the amine and the carboxyl group. Now, we need to add another PAS molecule, creating a link between the OH and the COOH groups. We have a few possibilities, any choice will be also good as long as you add another benzene linking OH and COOH groups. I choose the COOH on the right-hand side to react with the new OH. This forms the ester group. Finally, we add, at least, one N bond. I select 2, ensuring that the end bonds are different. In the second question of question 20b, we have the statement that the treatment of tuberculosis, the maximum daily dosage of PAS that should be prescribed is 300 mg per kilogram of body mass. A child weighs 20 kilograms. We are asked to calculate the number of PAS molecules in the maximum daily dosage of PAS for this child. The maximum dosage for 20 kilograms child is 300 times 20 is equal to 6,000 milligrams or 6 grams of PAS. As the molecular mass of PAS is 153 grams per mole, we get that 6 grams are 3.9216 times 10 to the power of minus 2 moles. Multiplying this number by Avogadro number, we get 2.36 times 10 to the power of 22 molecules. Question 21 is about alpha amino acids. In Part A, we are asked to explain the term optical isomer. Stereoisomers are molecules that have the same structural formula but differ in the spatial arrangement of their atoms. They form non-superimposable mirror images about a chiral center. Part B of question 21 is about the alpha amino acid valine, and we are given the radical group. In the first question, we are asked what is the systematic name of valine. The best approach for this question is to draw the formula of the compound. With the general formula for alpha amino acids given in Part A, and the given structure of the R group, we can draw the valine. Then, we select the longest chain and start numbering the carbons from the carboxylic acid. Then, the systematic name of the valine is 2-amino-3-amethylbutanoic acid. In the second question we are asked draw diagrams to show 3D structures of the optical isomers of valine. To draw optical isomers, first locate the chiral center. This is a carbon atom bonded to 4 different groups. In the given structure, carbon 2 is the chiral center. Next, visualize this carbon at the center of a tetrahedron, with each of its 4 different groups positioned at the vertices. To draw the optical isomer, simply create a mirror image of this tetrahedral structure. In question 21, Part C, the reaction involving 3 alpha amino acids yields compound E, whose structure is given. In the first question, we are asked how many optical isomers are possible for compound E. The number of optical isomers is given by the number of chiral carbon atoms bonded to 4 different groups. Each carbon is going to give 2 possible optical isomers. If the number of chiral carbon atoms is n, the number of possible optical isomers is 2n. In compound E we have 4 chiral carbon atoms. Therefore, the possible number of optical isomers is 2 to the power of 4 equals to 16. In the second question, a student hydrolyzes compound E with dilute hydrochloric acid. We are asked to draw the structures of the organic products formed by this hydrolysis. The reactions of the different amino acids can be explained as the reaction between the amino and the carboxylic group, producing an amide group and water. Hydrolysis is the reverse process. We identify the amide group and reverse the reaction. They have 2 amide groups in compound E and we have 3 alpha amino acids. To ensure you get full marks, bear in mind that hydrolysis is performed in an acidic medium, therefore we should protonate the ammonia. Question 22 is about reactions of acrolein. In Part A, acrolein reacts with sodium cyanide in acidic conditions and we have 2 questions. In the first question we are asked to outline the reaction mechanism for this reaction, showing the intermediate and the organic product. We are provided with the structure of acrolein, we need to include curly arrows and relevant dipoles. At A level, we should treat this as a nucleophilic addition to an aldehyde. However, while conjugate addition, or Michael addition, is a valid chemical reaction here and accepted on the mark scheme, it's not usually on the A-level syllabus. To play it safe and guarantee marks in the exam, stick to the topics taught in the A-level curriculum. However, we will see both reactions here. In the nucleophilic addition to an aldehyde, the cyanide ion acts as a nucleophile, attacking the electrophilic carbon of the aldehyde's carbonyl group. This carbon has a partial positive charge because the pi electrons in the carbon-oxygen bond are polarized towards the oxygen, which consequently gains a partial negative charge. The negatively charged intermediate is highly reactive and quickly reacts with an hydrogen ion. The conjugate or Michael addition occurs when an organic molecule with a carbonyl group and a carbon-carbon double bond are connected to each other separated by a single carbon-carbon bond. The pi electrons of the carbon-carbon double bond shift, and then the pi electrons of the carbon-oxygen double bond also shift onto the oxygen, forming an enolate intermediate. The enolate is then protonated by hydrogen ion to give the saturated nitrile product. In the second question, we are asked to name this type of mechanism. Given that a nucleophilic species has undergone an addition reaction with the initial product, this mechanism is classified as nucleophilic addition. In Part B of Question 22, we are asked to complete a given flowchart with reactions of acrolein. To convert acrolein into an alcohol, we have two possible reactions, the reduction of the aldehyde group or the hydration of the alkene. Since the first product shown is an unsaturated alcohol, the double carbon-carbon bond must remain unchanged. This means the reaction is reduction of the aldehyde group only, not hydration of the alkene. This is performed using sodium borohydride to obtain prop-2-en1-ol, or allyl alcohol. To form the diol, the alkene group in prop-2-en1-ol undergoes hydration. This is achieved using water steam as reagent and acidic conditions as catalysts, where you can write hydrogen ion, sulfuric acid or phosphoric acid. We have two possible products, propane 1,3-diol and propane 1,2-diol. To find the major product, we use Markovnikov's rule. When an unsymmetrical alkene reacts with an unsymmetrical reagent, the hydrogen atom adds to the carbon of the carbon-carbon double bond that already has the most hydrogen atoms. In this case, it is propane 1,2-diol. Acrolein can be converted into a carboxylic acid by oxidation of the aldehyde group. The reagent is acidified dichromate 6 and the product formed is prop-2-enoic acid or acrylic acid. The carboxylic acid is converted into an acyl chloride by reaction with thionyl chloride. The product obtained is 2-propenyl chloride or acryloyl chloride. Acrolein can form a polymer via addition polymerization using the carbon-carbon double bond. When drawing the polymer, break the carbon-carbon double bond to a single carbon-carbon bond, then join repeating units together. Show 2 repeat units as required. In question 23, we are given the results of an unknown organic compound. We know that the addition of 2,4-dinitrophenol does not produce visible change. We are given the elemental analysis by mass. The mass spectrum shows a molecular ion peak at m/z equals 144. We also have the infrared spectrum and the NMR spectrum. With this information, we are asked to identify the organic compound, showing our reasoning. These questions are like puzzles. We identify the different parts of the compound and then fit them together to determine the full molecule. As the addition of 2,4-dinitrophenol does not produce visible change, we can discard aldehydes and ketones, as their present would produce an orange precipitate. From the elemental mass analysis, we can work out the empirical formula. I've included a link in the description explaining how to calculate empirical formulas, with practice questions. First, divide the mass or percentage of each element by its atomic mass to find the number of moles. Then divide each value by the smallest number of moles to get the simplest whole number ratio. This ratio gives the empirical formula. This gives an empirical formula of 4 atoms of carbon, 8 of hydrogen and 1 of oxygen. The relative formula mass of this empirical unit is 72. As the mass spectrum shows a molecular ion peak at 144, we can see that the molecular formula is going to be twice the empirical formula. This means 8 atoms of carbon, 16 of hydrogen and 2 of oxygen. We now focus on the infrared spectrum. Using the data sheet for the exam, we can see that the peak around 3000 reciprocal centimeters is due to carbon-hydrogen bonds. The peak around 1750 reciprocal centimeters is due to a double carbon-oxygen bond. Due to 2,4-dinitrophenol, we know that it is not an aldehyde or keton. Carboxylic acids present a broad peak between 2500 and 3300 reciprocal centimeters. We have a peak at around 3000 due to the carbon-hydrogen bond, but it is not broad. We can discard carboxylic acids. As we don't have nitrogen or chlorides, we can discard amides and acyl chlorides. As the molecular formula has only 2 oxygens, we can discard acid anhydrides that contain 3 atoms of oxygen. The only option left is an ester that it is compatible with 2 atoms of oxygen. The peaks below 1500 reciprocal centimeters are considered fingerprints. We move now to the proton NMR spectrum. Using the data sheet for the exam, we can see that the peak with shift at 0.9 refer to a carbon-hydrogen bond with an area proportional to 9 hydrogens, and as it is a singlet, means that the adjacent carbons have no hydrogens. This is consistent with a terp-butyl. The peak at 1.2 ppm is correspond to a carbon-hydrogen bond with an area relative to 3 hydrogens. As it is a triplet, the adjacent carbon has 2 hydrogens. This is the profile of the methyl part of an ethyl. A quartet between 2.0 and 2.3 ppm integrating to 2 hydrogens, consistent with a CH2 group adjacent to a carbonyl group. The quartet splitting confirms coupling with 3 neighboring protons, matching the methyl group at 1.1 ppm. A singlet at 4.1 ppm integrating to 2 hydrogens indicates a CH2 group linked by a single bond to an oxygen and to another carbon with no hydrogens. With all this information, we need to fit together the different fragments to build the full molecule. I start with the ester found via the infrared spectrum. On the left-hand side of my structure, we can see that the NMR fragment at shifts 2 and 1.2 ppm fits nicely. On the right-hand side of the fragment that we have, we can fit the fragment from NMR at shift 4 ppm. To finish, on the right-hand side, we can add the NMR fragment at 0.9 ppm. Counting the number of atoms, we get that the structure fits the molecular formula. Just tidy up a bit, and we have that the compound is terp-butyl ethanoate or 1,1-dimethylethyl ethanoate. Alright, that's the full paper done. If you made it this far, seriously well done. Working through full exam questions is one of the fastest ways to improve your grade. Remember, focus on how the mark scheme thinks, practice the wording of your answers, and revisit any questions that challenged you today. If this helped, hit like, subscribe for more OCR chemistry walkthroughs, and drop a comment with the next paper you want me to cover. Good luck with your revision, and I'll see you in the next one.